This is a security scan of 9 microservices. So there's 30 findings, a critical remote code execution advisory on every single one of them. At my day job, I watched a scanner do this across a real fleet, about 150 hits, 1 CVE everywhere. The real number of services that needed fixing was actually just 1. This video is about the gap between those 2 numbers because that gap is where remediation programs go to die. So before I open another terminal, let me show you the shape of the problem that I want to take a look at today. There are 9 little .NET services, payments, orders, inventory, all the usual suspects. And I rebuilt the whole situation as a public demo you can clone. There's a link below. So every one of them depends on the same internal SDK package. That SDK is frozen at version 1.4.2, built in 2019, and the team that owned it doesn't exist anymore. If you've worked anywhere with more than 50 repos, you have one of these. Nobody bumps it because nobody owns it, and it works. So here is what that pin actually drags in. 3 package references from 2019, and every one of them carries a known advisory, including a critical RCE in the text encoding package. And the build knows sometimes. Build the ledger service, and NuGet's audit prints the warning right there in the log. Known high severity vulnerability. But that only fires for packages as service references directly. Everything the frozen SDK drags in, the build says nothing. Everyone's been scrolling past the one warning they did get for years. Now, put a scanner on this fleet. Every .NET service publishes a file called deps.json, the compiled record of its dependency graph. The scanner reads that file, sees system.text, .encodings, .web 4.5.0, looks it up, and files the critical finding. It reads the guest list, but it never opens the box. In this demo, the scanner is played by 2 open source tools you can run yourself. Sift builds the package inventory from that manifest, and Gripe here matches the inventory against the public advisory databases. That 2-step inventory the match is how basically every scanner works, free or 6 figures. The only question is what the inventory is built from. So 9 services, same SDK, same manifest entry, 9 criticals, plus the highs. Here is that exact scan running for real. One script in the repo builds and scans the whole fleet, tools pinned, so you'll get the same wall I got. That's the wall of findings, right here. And on a dashboard, it looks like 5 alarms fire. So, is it real? The manifest says 4.5.0 ships. The disk says 8 point something, patched years ago, right? No issues here. So here's the mechanism, and it's simpler than it sounds. Back in 2019, you got this library from NuGet. So the SDK pinned it like any other package. But on modern .NET, this exact library now ships inside the runtime itself. Every .NET 8 box already has the patched copy built in. So at build time, .NET sees the ancient request, says, I already have a newer one of those, and ships nothing. The app runs on the runtime's patched copy, but the manifest is a record of what was asked for, not what was delivered. The order form says 2019. The box actually contains the patched version. And the scanner only ever reads from the order form over here on the left. And checking the disk isn't magic either. That's just trivia with default settings. which inspects the image's file system and reports only what actually gets shipped on the right over here. So same image, two tools, two completely different answers, and that disagreement is how I found out which findings were real. Don't take my diagram's word for it. Let's open up one of these containers. There's the manifest entry. The scanner isn't hallucinating. The file really says 4.5.0. And there's the disk. One copy in the shared framework directory, version 8 point something. The vulnerable version 4.5.0 is nowhere in this image. To use an analogy, the scanner is reporting the guest list, not actually who showed up. Modern open source scanners Trivy, Sift, Gripe quietly fixed this whole false positive class. Their current defaults check whether a DLL actually ships before they report it. So out of the box, they call this fleet clean. I had to set a documented config flag in Sift telling it to trust the dependencies.json blindly, just to reproduce the wall of findings you saw in the cold open. With that, the free tools already concede that manifests lie. Some of the expensive platforms are still reporting the guest list. So, all false positives, close the tickets, go home, right? No. And this is the second half of the lesson. A finding your auditor can see is real, whether or not the DLL ships. Nobody reviewing your compliance report is going to do Docker image archaeology on 90 services. And you can't tell the phantoms from the real ones without doing the investigation, which is exactly what makes this expensive. Because in my wall of 30 findings, one of them is not like the others. So the ledger service is the straggler here. It's still on .NET Core 3.1, end of life runtime, end of life base image. And it pins newtonsoft.json 12.0.1, which, unlike the phantoms, actually ships in the image. Same test we ran on payments, opposite verdict. List the app folder inside the shipped image, and there it is, newtonsoft.json.dll sitting right next to the app. Vulnerable DLL physically present on a runtime that stopped getting patches in 2022. This is the one. Now watch how fast the actual fix is once you know where to aim. What you're watching is a Claude Code session making 3 one-line edits. The ledger project file jumps from the dead .NET Core 3.1 to .NET 8. The Docker file's runtime base image jumps with it. In the Newtonsoft version, pinned once, in the one file that sets versions for the whole fleet, goes from 12 to 13. Then the same CI style build we've used all episode rebuilds the image, and the same 2 scanners rerun against it. Shipped DLL view, clean. The vulnerable DLL is gone from the image we just rebuilt. The fix took minutes. Knowing which service to fix is what took the investigation. So that leaves the phantoms, and the fix there isn't ignore them. The manifest is lying about what ships, so make it stop lying. Pin the patched versions explicitly, rebuild, and the manifests match reality. The findings clear on their own. This diff is that fix for one service. 3 added lines, 1 explicit pin for each package the frozen SDK was lying about. So the manifest finally tells the truth about what ships. And it's the same 3 lines in every service. Watch the same diff repeat across the fleet. Doing that across 9 demo repos is a loop. Doing it across a few hundred real ones is a job for a fleet of agents. And that's a future episode. The lesson isn't scanners are dumb, and it isn't trust the scanner. It's that a finding is a claim, and claims about what's vulnerable have to be verified against what actually ships. The scanner said 150. The truth was 1, but proving that is what saved weeks of blind patching. Everything you saw is in the repo link below, deliberately vulnerable, ready to scan. And if you want this whole workflow, the triage, the verification, the agents running at your own org, that's the thing I can help teams set up. Links below as well. Next episode, how I run a whole fleet of Claude Code sessions against one backlog without them trampling each other.